Two movements lead to the paradigm change. The first movement is characterized by a new social reality, as shown in this slide. The second movement is due to a novel theoretical basis for science, as shown in the next slide. It is primarily the computer which has changed our social reality. Especially, two computer developments are responsible for the wind of change. The first is the enormous storage capacity which emerged in the cloud. We talk about the magnitude in petabyte scale. 1 petabyte is equal to 1 quadrillion bytes or 1000 tetrabytes. This is 10 to the 15th bytes. Google processes about 24 petabytes per day. The second important development is that a huge number of computers are now connected via the internet. We now have the access to the huge data amount from many locations. In addition, we have Twitter, Facebook, and many other social networks which give a context for the enormous data amount. We have a data flooding. This is a problem normal science cannot solve. The structures of the science world were designed to fit a pre-computer age. Established power structures do not easily adopt. As a consequence of the developments of the computer and its networks, a revolutionary science develops. In line with this, we can see do-it-yourself and open science projects on the internet. A novel, data-driven research concept is under development. On the theoretical side, new theories for dealing with huge data amounts and complex systems have emerged. We can follow this development back to the Greek idealistic philosopher Plato. He introduced in his dialogue Philebus a concept called system. A system is, according to Plato, a model for thinking about how complex structures are developed. System meant total, crowd, union. Another idealistic philosopher, Kant, introduced in 1790 in his Critique of Judgment the concept of self-organizing. Kant stated, there exists an entity whose parts or organs are simultaneously end and means. Between the 1950s and 60s, 3 groundbreaking works were published. 1948, Norbert Wiener publishes Cybernetics or Control and Communication in the Animal and Machine. In 1955, William Ross Ashby's Introduction to Cybernetics came out. 1968, Ludwig Bertalanffy publishes General Systems Theory, Foundations, Development, Applications. Bertalanffy defines the concept of systems. Cybernetics explain complex systems that exist of a large number of interacting and interrelated parts. Wiener and Ashby pioneered the use of mathematics to study systems. This system theory was further developed in the following years. Important contributions during the 70s and 80s were the theory of second-order cybernetics with prominent figures such as Heinz Förster. He found out that an investigator of a system can never see how it works by standing outside, because the investigator who observes a system affects it and is affected by it. The role of the investigator as a part of the system, self-referencing, self-organizing, and the subject-object problem were in focus. Moreover, to mention is a Nobel Prize-winning work of Ilya Prigogine on self-organization and his system theory concepts with thermodynamics. Furthermore, Mitchell Feigenbaum's work on chaos theory. General systems theory is an important fundament for software. Thus, if we use a computer as a scientific tool, the systems theory influences the scientific method. This means, by using the computer as a scientific tool, we are applying a theory based on idealism. The algorithms of our computer models are finally based on platonic idealism. Contemporary application finds systems theory in bioscience fields such as systems biology and its practical application, synthetic biology. The term systems biology was created by Bertrand Laffey in 1928. Systems biology focuses on complex interactions in biological systems by applying a holistic perspective. So we saw that the described philosophical movement has two components: idealism and systems theory. Idealism will be explained in this slide. Basic concepts of systems theory in the following slides. Philosophical idealism has its ancient roots in the work of Plato, who lived from 428 to 348 before Christ. A centerpiece of Plato's work is the theory of forms, also called theory of ideas. Plato claimed that the material world of change, which we experience with our senses, do not possess the highest and most fundamental kind of reality. Only inferior things of this world, such as material objects, mirror images, and shadows, are knowable through our senses. This inferior world is object to constant change. On the contrary, we have an internal, static world. This superior world consists of mathematical objects, terms, and non-materialistic abstract forms or ideas. These are the only true objects of study that can provide us with genuine knowledge. Forms are archetypes, blueprints, the essence of the various phenomena of the same thing. Moreover, Plato believed that forms are the fundamental building bricks of our world. Cybernetics follows this line of thinking. The base of cybernetics is the assumption that reality is not reflected but calculated by the human nervous system. This means, for our example on the slide, our brain calculates a model of an object such as DNA. The human reception is the basis of the scientific method. The key tools are mathematics and logic. The result of this calculation is a model of DNA which is not identical with the object DNA. It is impossible to achieve knowledge about the world such as it exists independent of us. Our human reception of reality is an invention of our brain. Heinz Förster states, in line with this, that all scientific theories are based on such inventions, which he provocatively called funny and interesting stories. The scientific proof is impossible. Hypotheses are inventions of our brain. If there's a hole in the theory, a new part is invented. Logic and mathematics are descriptive machines which are used to deduce one statement from another. All statements are true because all are deducible from each other. This is a chain without an end. Seen together, we do not have access to the reality of objects such as they exist outside of us. The word science has its Indo-European root in the word psi. This means separating. Psi belongs to a reductionistic world of thinking. Heinz Förster saw an end to the 2000-year movement started with Aristotle. He stated, if you take in account all systems theory and systems researchers which appear today in art and science, I would not call this science any longer. I would call systemics. Contemporary science moved to a position which sees things together, short systemics. Thus, from science to systemics. This is how I see the steps today. A system is a set of interacting or independent components forming an integrated whole. Common characteristics of a system are components, behavior, and interconnectivity. Systems have a structure defined by components. Systems behavior involves input, processing, and output of data. Behavior can be described with terms such as self-organizing, dynamic, static, chaotic, strange attractor, adaptive. Systems have interconnectivity. This means that the parts of the system have functional as well as structural relationships between each other. The stipulated line marks the boundary of the system. Boundaries can be open or closed. As a consequence of this boundary, the system is distinguishable from its surroundings. A system can be self-regulating by feedback. Such feedback can be given, for example, by scientific experiments or communication in computer networks. It is important to be aware of the context of the system. In this respect, a researcher can be described as a part of the system. To summarize, computer cloud storage, networks, and systems theory are the fundament of a new scientific method, data-driven systemics. We will in the following examine the concept of data-driven science and the consequences of this concept for our everyday life as scientists.